Hello, and welcome to this edition of the Commission's webinar series. My name is Jordan Van Bazouw, and I'm the Supervisor of Drilling and Production at the BC Oil and Gas Commission. I'm pleased to be your host today as we explore some commonly used well decommissioning practices. And please note that this webinar will be available on the Commission's website at bcogc.ca. To turn on closed captioning, please click the icon circled in red as shown on the slide. If you have questions, be sure to email them to stakeholder@bcogc.ca. As you can see, there's a lot of information to cover today, beginning with an overview of why this is important. We'll be looking at the anatomy of a well from well construction through to production and onwards, and also looking at the regulations and guidance governing the practice of well decommissioning in British Columbia. We'll look at some very specific well plugging techniques, also known as zonal abandonment, and some remediation techniques, including both some common and not so common practices. And at the end, an overview of what it means to complete surface decommissioning at a well. The role of the BC Oil and Gas Commission is to oversee activities of the oil and gas industry, from exploration and development to pipeline transportation and reclamation. Our role has recently expanded to include refineries, value-added gas and liquids manufacturing processes, and some aspects of geothermal power. Well decommissioning is an important step on the road to site reclamation, as wells must be plugged in a manner that ensures they don't pose a threat to people or the environment. Let's begin by looking at the anatomy of a well, from well construction through to production. Well construction begins with the drilling of a well. Here, a drilling rig is installed over the location a well will be drilled. A drill bit at the end of a drill pipe crushes the rock and is periodically pushed deeper by adding sections of pipe to the drill pipe. Meanwhile, drilling mud or drilling fluid is circulated by pumping down the inside of the drill pipe through the drill bit and returning to surface along the outside of the drill pipe. This removes the crushed up pieces of rock that would otherwise cause drilling to stop by seizing against the drill bit. This process continues until drilling has reached the target formation. Once drilling has finished, the well is now little more than a very deep hole in the ground. To provide some structural stability, casing would then be installed. Casing is metal pipe installed in a well that is usually cemented in place, as opposed to tubing, which is metal pipe installed or used in a well or well operation that is not cemented in place. Similar to how drilling fluid was circulated during the drilling phase of the well, cement can be circulated by pumping down the inside of the casing string and returning to surface along the outside. At the end of that operation, the casing string has been surrounded by a cement sheath that extends from the bottom of the well to surface. Once the final casing string has been installed and cemented in place, the well is ready to be completed. Completions is a catch-all term describing the events, modifications, and equipment necessary to allow a well to begin producing. A completed interval is a geological layer that is or was at one point capable of production. The most common completion technique, known as perforating, uses small explosive charges to punch holes through the casing and the cement sheath to create a pathway from the reservoir into the wellbore. In the example shown here, the area highlighted in red is the completed interval. In addition, a tubing string equipped with a bottom hole pump is installed in the well, and a pump jack is installed at surface, which provides power to the downhole pump, allowing oil, water, and gas to come to surface. A well might produce in this configuration for many years or even decades, depending on the producing characteristics of the well. At the end of a well's producing life, it's ready to be decommissioned. Let's begin by looking at the regulations and guidance covering the practice of well decommissioning in British Columbia. The Drilling and Production Regulation, or DPR, is a regulation that establishes, among other things, the expectations permit holders must meet when decommissioning wells. These requirements are results-based and include things like establishing adequate hydraulic isolation between zones, ensuring that fluids will not leak from the well, and that the long-term integrity of the wellbore is maintained. It's important to note that the DPR does not establish timelines for well decommissioning. Those expectations are established under the dormancy and shutdown regulation. Because the requirements in the DPR are results-based, the Commission has also provided more detailed guidance for how permit holders may meet the expectations established in the DPR. The Oil and Gas Activity Operations Manual is one of many pieces of guidance published by the Oil and Gas Commission for use by permit holders. Where the Drilling and Production Regulation may have results-based requirements, the Operations Manual goes into much more detail about how permit holders are expected to meet those regulatory requirements. It can be thought of as the Commission's suggested means of meeting the Drilling and Production Regulation. With respect to well decommissioning practices, the Operations Manual currently directs permit holders to follow the Alberta Energy Regulator's Directive 20. Directive 20 contains instructions for permit holders, which in Alberta are known as licensees, that are decommissioning wells in Alberta. There are very specific prescriptive requirements in Directive 20, including things like plug placement, pressure testing, and a host of other factors that are involved in the process of well decommissioning. While Directive 20 is tailored to Alberta's regulatory environment, the technical principles from Directive 20 have been adopted for guidance for permit holders that are decommissioning wells in BC. The Commission recently published new guidance for permit holders decommissioning wells in British Columbia. Effective January 1, 2022, the BC Well Decommissioning Guidelines will be replacing references to the Alberta Energy Regulator's Directive 20. This new guidance includes references to industry recommended practices, or IRPs, and establishes new requirements for permit holders decommissioning high-pressure wells. These changes are being implemented to respond to emerging trends seen in the practice of well decommissioning in British Columbia. You may have noticed from the regulation and guidance overview that the terms abandoned and decommissioned were being used somewhat interchangeably. The term abandoned has a long history of use in the oil and gas industry, and historically has applied to both downhole plugging and surface cutting and capping of a well. You can imagine the term abandoned has some baggage attached to it, and it's not uncommon for abandoned wells to be confused with orphaned wells, which is where the permit holder is either insolvent or cannot be located. Within the context of the BC Well Decommissioning Guidelines, however, the term abandoned has been reserved for downhole plugging activities only. For instance, where a completed interval is plugged, we say that that zone has been abandoned. Well decommissioning, on the other hand, is a term that's been adopted more recently, including within the dormancy and shutdown regulation. Within the guidelines, well decommissioning refers to the process as a whole, which can include combinations of many different activities, including zonal abandonment, remedial activities, and surface decommissioning. However, it's important to note that well decommissioning is not the term used in the Drilling and Production Regulation. That regulation still refers to well abandonment. Now, let's explore some commonly used well plugging techniques, including those that are used for zonal abandonment of a completed interval. The well shown here has reached the end of its productive life. You can see that the tubing string, bottom hole pump, and pump jack have all been removed. Let's take a closer look at the completed interval, because that's where most of the action happens when doing a zonal abandonment. In this case, the permit holder is choosing to use the most common technique used for zonal abandonment, which is to install a bridge plug and cement cap above the completed interval. A bridge plug is a tool used to completely seal off the wellbore, preventing any flow of gas, oil, water, or other fluids either upwards or downwards past the bridge plug. Now that description doesn't on its own provide a whole lot of insight, so let's take a closer look at the bridge plug itself. Shown here is one example of a bridge plug, and I'd like to highlight a few of the components. First is the mandrel, the inner core of the bridge plug around which all other components are installed. In yellow at the top and bottom are the slips, and in the middle of the bridge plug in black is the sealing element. This tool is installed by applying a compressive force along the axis of the bridge plug. This causes the slips to slide outwards along the sloped shoulders and get pushed outwards into the walls of the casing. The slips are made of a hardened steel and engage very strongly with the casing. This prevents the bridge plug from sliding upwards or downwards within the wellbore. In addition, the compression pushes the sealing element outwards, and it also engages with the walls of the casing. This sealing element prevents fluid from passing upwards or downwards past the outside of the bridge plug. In addition, because the mandrel has a plug at the bottom, it prevents any fluids from passing through the inside of the bridge plug. Coming back to our example well, the permit holder has placed a bridge plug above the completed interval. This prevents any future flow of gas, oil, or water from the completed interval. However, to permanently plug that completed interval, a cement cap must also be placed on top of the bridge plug. The most common technique for placing a cement cap on top of a bridge plug is to use something called dump bailing. Dump bailing is a technique used to place small volumes of cement or other liquids in a wellbore on top of a plug. In this case, when we refer to a small volume, that's still the equivalent of 8 vertical meters of cement on top of the bridge plug. Dump bailing can be thought of as a very long, very narrow bucket with a glass bottom. If that very long, very narrow bucket with a glass bottom were filled with a cement slurry, slowly lowered into the wellbore, and then dropped sharply onto the bridge plug, the glass bottom breaks and all the cement slurry slides out the dump bailer and comes to rest on top of the bridge plug. And what you're left with is a cement slurry that hardens to form a permanent plug on top of that bridge plug. In some cases, a completed interval is classified as either a high pressure or a level A interval, both of which result in higher consequences should that zonal abandonment plug fail. As a result, a more robust abandonment plug is required. Permit holders can still begin by setting a bridge plug above the completed interval, but dump bailing cement is no longer an appropriate technique for placing that cement cap. Instead, a cement cap must be circulated in place. A tubing string is run into the well until just above the depth of the bridge plug, and cement is circulated by pumping down the tubing string and up the outside of the tubing string. However, rather than pumping cement to surface, a 60-meter cement cap is placed on the bridge plug, after which the tubing string is withdrawn, resulting in that more robust abandonment plug for those higher consequence intervals. Let's go back to the bridge plug for a moment. With a few small modifications, this tool can be transformed into something known as a retainer, which can be used for different types of zonal abandonment plugs and can also be used for wellbore remediation. A cement retainer is a tool used to apply treatments to a lower interval while isolating from the space above, and it does this thanks to a couple of key differences from a bridge plug. First of all is the presence of a retainer valve, which here is shown in the closed position. When that valve is in the closed position, it acts just like a bridge plug in that no fluid can pass through the inside or the outside of the cement retainer. The second change is the presence of ports, which are holes through which fluids can flow once the retainer valve is open, as shown here. A cement slurry pumped through the inside of the retainer would pass through the retainer valve, through the ports, and into the wellbore below the retainer. At the end of the job, the retainer valve is brought back into the closed position, as shown here, which then prevents any further flow of fluids either upwards or downwards past the cement retainer. In the example shown here, a permit holder is preparing to conduct a cement retainer squeeze. They engage with the already set cement retainer with a tubing string and begin pumping cement down the inside of the tubing through the retainer. The cement is then directed into the perforations, and by applying pressure, those perforations are filled with cement. After conducting the squeeze, permit holder disengages from the cement retainer and begins circulating a cement cap in place. Similarly to what we've seen before, cement is pumped down the inside of the tubing, but this time can return up the outside of the tubing string. A 60-meter cement cap is circulated in place, after which the tubing string is withdrawn, and the cement retainer squeeze and cement cap are complete. Another technique for zonal abandonment is circulating a cement plug across the completed interval. In the example shown here, the permit holder takes a tubing string and extends it to below the bottom of the completed interval. Cement is circulated down the inside of the tubing and up the outside of the tubing until a plug extends from 15 meters below the completed interval to 15 meters above the completed interval. Afterwards, the tubing string is withdrawn, leaving a circulated cement plug that extends over the entirety of the completed interval. In some cases, a permit holder might conduct a cement squeeze with a circulated cement plug. By applying pressure from surface, the cement plug is forced into the perforations. This increases the contact area between the cement plug and the completed interval, improving the overall quality of the zonal abandonment plug. One unique attribute of circulated cement plugs is that a single plug can be used to abandon multiple completed intervals. In that case, a tubing string is run past the bottom of the deepest completed interval, and cement is circulated down the inside of the tubing and up the outside of the tubing until a cement plug is placed that extends below the bottom of the deepest to above the top of the uppermost completed interval. After the tubing string is withdrawn, you have one circulated cement plug abandoning two completed intervals. So to summarize, permit holders typically use one of three techniques for conducting zonal abandonment operations: either a bridge plug with cement cap, a cement retainer squeeze, or a circulated cement plug. In the example shown here, you can see that a permit holder has abandoned the completed interval by setting a bridge plug and capping it with cement. Well decommissioning is much more than just zonal abandonment. In some cases, well remediation must take place to address a wellbore integrity issue. Now, we're going to explore some of those commonly encountered issues and what techniques permit holders have available to address them. Well conditions requiring remediation can generally be broken out into three different categories. First, casing failures, where the casing that was cemented in the well is no longer able to contain the pressure exerted by the wellbore fluids. Second, surface casing vent flow or gas migration, where a flow of gas exists outside the cemented surface casing. Or third, groundwater protection, for instance, if the base of usable groundwater was not covered by cement at the time the casing was first installed in the well. When remediating a well with a casing failure, permit holders have a variety of techniques at their disposal. Depending on the characteristics of the failure, including whether a repair or simply isolation is required, permit holders can choose to use a bridge plug and cement cap, a cement retainer squeeze, or a circulated cement plug. In the example shown here, the permit holder has elected to isolate the casing failure by placing a bridge plug and cement cap just above the location of the casing failure. Remediating a surface casing vent flow or gas migration is not as straightforward as fixing a casing failure. Because the flow of gas exists outside the casing string, merely plugging the inside with a bridge plug and cement cap would not solve the underlying issue. As a result, permit holders are limited to either conducting cement retainer squeezes or circulating cement if the primary cement job was not successful. In the example shown here, the permit holder has perforated at the source of the surface casing vent flow, installed a cement retainer, and conducted a retainer squeeze into that source interval. Following the capping of the retainer with cement, the remediation of the surface casing vent flow is complete. A similar approach can be taken with gas migration. In some rare cases, particularly for older wells where the production casing was not cemented to surface, additional remediation to protect groundwater might be required. Similarly to surface casing vent flows and gas migration, merely placing a bridge plug and cement cap inside the casing would not solve the underlying issue. As a result, when conducting groundwater protection remediation, only circulating cement or cement retainer squeezes are appropriate for addressing the issue. In the example shown here, because the surface casing covers all intervals above the base of usable groundwater, no groundwater protection is required. Once all the necessary downhole activities have been completed, including zonal abandonment and, if necessary, remediation, surface decommissioning activities can take place. Surface decommissioning consists of two steps: cutting and capping. To cut the wellhead off, the wellhead, casing strings, and cement sheaths are cut off at a depth of 1 to 2 meters below ground level. This is typically done in one of two ways, either with a jet cutter, where a tool is lowered into the wellbore and cuts everything off from the inside, or by excavating a hole around the wellbore and cutting everything off from the outside with a welder's torch. Once the wellhead, casing string, and cement sheaths have been cut off, metal plates are installed onto the casing strings to prevent anything from falling back into the well. After those plates have been installed, the area around the well is backfilled and graded, resulting in a flat site. At this point, the well itself has been decommissioned and the site can proceed to the next step, reclamation. And that brings us to the end of today's webinar. I'd like to thank you for joining me on this high-level overview of well decommissioning practices, and a special thanks to Weatherford for their use of their downhole equipment diagrams for bridge plugs and cement retainers. As you can imagine, there's lots of information out there, so I'd encourage you to go to the BC Oil and Gas Commission's website at bcogc.ca for links to some of that information. And lastly, if you have any questions, please feel free to email them to stakeholder@bcogc.ca. Thanks again. Hope you have a great day.